Be right back. That webcam they were malfunctioning. Yeah, Osseous, can you hear me? I'm just checking the audio real quick. The webcam here malfunctioned, so I want to make sure that. Not social media. Hello, hello. Okay. Okay. It's 8:30. Let's go and get started. Good morning, everyone. How are you guys doing today? Doing okay, doing okay. I went to a wedding over the weekend, so it was actually on Easter Sunday. It was one of my best friend's weddings. I was the best man, so I gave a speech, but I also drank copious amounts of alcohol. One thing that I've learned as we're getting older is that it takes longer and longer to recover from drinking alcohol. So it was a couple days ago, but I'm still feeling the effects a little bit. So if I'm a little bit low energy today, I apologize. I should be better by Thursday. Okay, so the plan for today is we're going to continue on with our lecture notes on Fourier series. And so we're going to finish up Fourier series today. And then probably what we'll do after that, we'll start Fourier transform. So I'm guessing it's going to be about half. Okay. So I have a couple more examples from Fourier series. Hopefully that's going to help us out with the homework. And then we'll start the Fourier transform stuff. Okay, so just a reminder, homework 5, the due date was pushed back for that. And so originally it was due this Wednesday. But because we didn't quite finish everything last week like I thought I would, the due date for homework 5 is pushed back until this Friday. Okay, so you have until this Friday to get that done. And then after homework 5 is due, I have one more homework assignment. It's the homework 6 is very short. It's just on the Fourier transform stuff. And then we'll have our midterm after that. So I think originally our midterm exam was planned for next Thursday, but because we're a little bit behind, I'm going to go ahead and push that back a week. And so the midterm is not going to be next Thursday; it's going to be the Thursday after that, just so you guys have some extra time to study, and we'll get some homework solutions. Okay. Okay. All right. So for those of you joining on Zoom, I apologize for kind of a weird setup. My camera is like literally just right next to my left hand. The webcam in the classroom decided to break today because why not? And so I got the webcam from my office, but the wire is very short, and so I have to kind of put it right here. And it's for audio purpose, just to make sure that everyone on Zoom can hear me, right? Okay, I'm going to assume yes. Okay, good. Okay. All right. So let's go ahead and get started. Are there any questions I can answer before we get started for today? All right. Let me write down all the announcements I said. Just so people. Homework 5. Do this Friday. Homework 6. Do next Friday. Short assignment. And then midterm 2. Thursday. Week 14. Okay. And so if you're not if you haven't seen the calendar right now, we're currently in week 12. We have just about a little bit over 2 weeks until the next. Okay, so that's basically our schedule for the next couple of weeks. And then after the second midterm, we have basically what we're going to cover for the rest of the class is probability and statistics, which is really cool stuff. Okay, let's go and get started today. And we're continuing our topic from last time, which is Fourier series. Okay, so let's start with a little bit of a review. So remember, the whole idea with Fourier series is that we are looking to represent functions in a different way, specifically periodic functions. Okay? And the way that we're representing our functions is that we're representing it as an infinite summation of sine and cosine terms. Okay. And so it looks like this. And so if we have some function, f of t, okay. So f of t is just some generic function. So it could be any periodic function. The only requirement is that it has to be periodic. What we're saying is that this is equal to a naught plus summation from n is equal to 1 to infinity, a n sine and pi t over L Bn sine of n pi t over L. For L here, L is an important parameter. L is our half period. So remember, whatever the period of our function is, L is just going to be half of that. Okay. And the other thing that's important here are, first of all, the coefficients. That's essentially what we're solving for. Or whenever someone says to solve for a Fourier series, the coefficients are what you want to solve for. Okay. And if you remember, when we first started talking about Fourier, we talked a lot about, volume and pitch in terms of its connection with sound. Okay. And so remember, the coefficients, what they represent is the volume, or in other words, the magnitude of those particular frequencies. And the other part of the Fourier series are these terms. And so these terms are the frequencies of our Fourier series expansion. Okay. And notice how they're linked. So with the exception of A0, which we'll talk about today in a second, but there's a link, right? And so for every value of n, is going to give us a different frequency, right? And so n is equal to 1, that's going to give us a certain frequency. N is equal to 2 is going to give us another frequency. And that's associated with a coefficient. Okay. And so the first thing I want to talk about today, and this kind of has to do with, I think, the second to last homework problem, is this idea that these two things are paired. And so it's a little bit hard to see in this form because it's n pi over L, but because that's the coefficient in front of the t for the sine or cosine term, that's a frequency. Okay. And so for any particular value of n, so n is equal to 1, 2, 3, or 4, that's going to give you two things, right? So it's going to give you a frequency in the expansion as well as its corresponding coefficient. And so for instance, so for n is equal to 1, that's going to give us a frequency which is pi over L. Okay. And then its corresponding coefficient, A1, is going to represent how strong that frequency is. Okay. Because when you're talking about any kind of generic signal, okay, so let's use sound as an example, because that's not the most tangible. Okay. Like we talked about before, complex sound, like human speech, is made up of lots of different frequencies that change, very, very rapidly, right? But at the same time, there are still certain frequencies in the sound that stand out more than others, right? So that's why, Alvin the Chipmunk sounds different than, Christian Bale as that, right? So Alvin has much higher frequencies. And so the coefficients that are associated with those higher frequencies are going to be much higher than others. And so because of this, this introduces this idea of a power, what's called a power spectrum. Right? So technically power spectrum is going to be talked about in Fourier transforms. But I think it's useful to talk about here so that we can connect the two. And so that's what I gave you. I think it's problem 3 in the homework, right? So problem 3, I gave you basically a frequency response graph. And what that shows you is basically a power spectrum. Okay? And so it looks something like this. So I'm going to go ahead and draw a graph like this. Okay? And for Fourier series, it ends up being kind of like a bar. Frequency 1, frequency 2, frequency 3, 4. So I'll do for 5 frequencies. Okay. Because in reality, the signal may look something like this, right? The real. It may look something like this. Okay, so some kind of like noisy signal with lots of different frequencies involved. And so when you take the Fourier series of that signal or that function, what you're going to compute in the Fourier series are essentially the coefficients or the frequencies and the corresponding coefficients for those frequencies. Okay? And so you may get something that looks like this. And so we have this. Frequency 3 is very strong. Frequency 4. Okay. So what this graph is showing us here is that frequency 3 or omega 3 is very dominant in the signal. Okay, so that's the frequency that kind of shows up the most or shows up the strongest. Whereas the other frequencies, maybe frequency 1, frequency 4, they don't really show up as much because their coefficients are low. Frequency 2, frequency 5 are kind of okay. And so what the height of these bars represent, they usually represent the values of the coefficients. So this would be like A1, A2, 3, A4, A. Okay. I'm going to assume B is 0 just for now, just for the sake of simplicity. Okay. And so if you were to reconstruct the signal, or just like the homework problem asks you to, and usually when you reconstruct the signal, you don't use all the coefficients, so you only use just a subset of the coefficients. Otherwise, your expression is going to be way too long. Okay. And so usually you're only going to use maybe the top 2 or top 3 or top 4 coefficients. So we can say f of t, our highest coefficient here is A3. So we're going to have A3 cosine of omega 3 t. Okay. Our next highest coefficient here is A5. So we have A5 cosine omega 5 t. And our next highest one is A2. So A2 cosine 2. Okay. But I want, the reason we're going over this is that, I want you to kind of, when you're doing Fourier series, I want you guys to always keep in mind that, these two things are pairs. So we're performing these integrals, we're getting these coefficients, but their values are paired directly with a value of frequency. Okay. And so another way that you can interpret the coefficients is that you can say that this coefficient represents how strong this frequency is in the original signal. Okay. I'm kind of using the terms signal interchangeably. So I'm going to try to say function, but function signal would be the same. So that's kind of a very important kind of conceptual understanding of what the coefficients represent. All right, any questions on this so far? Okay. All right, so that's an important interpretation. But if we go back to our original decomposition here, so that takes care of AN and BN. So A and BN, we kind of have a better understanding of what those represent now. But we have another coefficient here that's not associated with any frequencies, A0, right? So A0 is kind of off on its own, and it doesn't have a frequency associated with it. So a lot of times, this term here is called a constant. Okay. It's called a constant term because it's just a constant, right? So it doesn't depend on n, and when you compute its value, it just ends up being a number. Okay. There's a very specific interpretation for this constant term. Let's talk about that. All right, so let me write out the formula for A0, so we can see it again. So A0 is 1 over 2L integral minus L to L f of t d. Okay. So this particular formula, if you have very good memory from calculus, maybe you've seen this formula before, but honestly, I forgot. I forgot until I actually taught this class, and I looked at the text like, oh yeah, that's true. But this formula right here, it goes by another name. Okay? So from calculus. Okay. So this formula is the same thing as the mean value formula. And so if you want to compute the mean value or the average value of a function in a certain interval, this is the function, or this is the formula that you are going to use. And so with that, that kind of shows kind of the role of the constant term. Okay. And so when you have a periodic function which does not average to 0, and so in other words, the mean value is something other than 0, this A0 here is going to capture that mean value. Okay. And so represents the mean value of the function over a single period. Right. So that's it. There's nothing more special about the constant term. I've been hyping it up a little bit, but that's basically what's there. And so it's interesting to think about when you think about even and odd functions, right? And so remember when you have an odd function or you have an even function, that tells you right away whether some coefficients are going to be 0. Okay. In particular, for an odd function, if we know our function is odd, we know that A0 and AN are equal to 0. Okay. And so that tells us that an odd function, if you have kind of purely odd function, it's going to have an average value of 0. That's kind of nice trivia to know. Okay. So that is the constant term. Let's talk a bit about kind of combining Fourier coefficients for separate for multiple functions. Let's look at for cases when we have functions that are represented as sums or scalar multiples. Okay. So this concept here is going to bring back a little bit from Laplace, right? So maybe if you remember from Laplace, we talked about how Laplace is a linear operator, right? And so for a linear operator, if you have two functions, so let's say we have f of t and g of t. And let's say that we want to take the Laplace transform of their sum. Okay. Because Laplace is a linear operator, we can basically ignore scalar multiples, so we can just kind of factor those out, and we can break up summations into multiple terms. And so taking the Laplace transform of this is the same thing as taking A times the Laplace transform of f of t plus B Laplace transform of g of t. Okay. And so you almost distribute the Laplace operator throughout. Okay. So that's what it means to be a linear operator, is that you can kind of ignore. And the way I think of it in my mind is that you kind of ignore just any kind of scalar multiple or sums. The Fourier is the same. So Fourier is also a linear operator. And so if you have two functions, so let's say we have f of t and g of t again, okay? And if we take the combined functions, so we have a f of t plus b g of t. Okay. And let's say that we want to find the Fourier series coefficients of both for this entire function together. I say for the combined function. So you want to find the Fourier Fourier series coefficients for a f of t plus b g of t. Okay. The way you can do this is you can find the Fourier coefficients for f of t. Okay. So you do that first. Next, you can find the Fourier coefficients for g of t. Right, so you take both of those. Okay, so those should be a lot simpler because they're more simpler functions. Then the combined coefficients for the combined coefficients for the combined function is just a times the Fourier coefficients of f of t plus b times the Fourier coefficients of g of t. Okay. And so you just kind of combine them together. Okay. You basically combine them together in the exact same way as Laplace. And so your coefficients end up being also a scalar multiple and a summation. So this property is really useful because we know from last time that if you have like even and odd functions, then your calculations become a lot more simplified. Okay. And so if you have, let's say, a situation where you have an even function added to an odd function, okay, you can compute each one individually, and then that'll save you a lot of work, and then you just add them up together at the end. Okay. And so I'll do kind of a quick example. Okay, I'm not going to go through the actual computation of the coefficients, but you can definitely verify for yourself. Well, let's say we have a function f of t is equal to 4t squared plus 9t. Okay. And this is valid on the interval from -2 to less than t less than 2. So it's a periodic function that's going to repeat every 4 seconds. Okay. And so what we want to do for this function is we want to compute its Fourier series coefficients. And since our period here is 4 seconds, since we go from -2 to 2, our half period length is just 2. Okay. And so first, when you look at this function, we have a quadratic function and a cubic function, and they're added together. So, you might be thinking this is a mess, right? So this is going to take forever for us to compute. But if we make use of our properties here for sums and scalar multiples, what we can do is find the Fourier series coefficients for t squared, okay? Then find the Fourier series coefficients for t cubed, and then just add them together. Okay? And this is useful because t squared is an even function. So the Bn here is going to be equal to 0. Okay? Meanwhile, t cubed here is an odd function. Okay? We know a0, an equal to 0 for this one. Okay? And so for t squared, all you have to compute is just a0 and an. And then for t cubed, all you have to compute is bn. And in fact, these two don't even interact with each other. And so, the an is going to be just contributed strictly from the t squared, and the bn is going to be contributed strictly from the t cubed. Okay. And so this should save you a lot of work. Okay? Otherwise, you have to integrate a lot. And you're going to integrate, a lot of your intervals are just going to end up being 0. All right. So definitely make use of this. And so if you're given a function with kind of a complicated expression, see if you can break it up into sums and scalar multiples to make it a little bit simpler. All right. Any questions on this? Okay. All right. So there's one last concept to talk about with Fourier, and that's this idea of a half range expansion. Okay. So this is the very last problem on the home. Okay. So the idea of a half range expansion is that sometimes, we're given functions that are only defined on kind of one side of the domain, so one side of the vertical axis. So let's say, we have a function, and so let's say that our half period length here is L, but we're only given just the function on one side. So let's say that we're given the function this side. Okay. So this function only defined from 0 to L. So we'd still like to compute a Fourier series expansion of this, okay? But in order to do that, if you look back at our formulas, we need to know kind of how the function is going to look like on the other side of the axis. Okay. But we're not given that information. We're not given, what the function actually looks like over there. So we don't know if it's an even function. We don't know if it's an odd function. It might not even be either. It might be none of the two. Okay. And so in these situations where, we don't know what the function looks like on the other side, basically what we're going to do is we're going to pretend. Okay. So we're going to pretend we know what the function looks like on the other side. Okay. And we'll keep it simple. And so we're not going to, let our imagination run too wild. And so we basically have two cases. And so in the one case, we're going to assume that the function's even, that is basically reflected off that vertical axis. And the other case is going to be odd, where we've reflected off that diagonal line. And so we kind of have two possibilities. Okay. So let's draw out the even side first. So that's our normal function there. If we assume an even half range expansion, our function is going to look like this. Okay. So it's basically just a mirror image across the vertical axis. For an odd half range expansion, it's going to look something like. And so we have our typical function here, our original function from 0 to L. Okay. And then for odd, remember, we're going to reflect off this diagonal line. Okay. And so function would look like this. Okay. And so if we make these assumptions, and so we assume that the function is going to look one way or another, we can compute its Fourier transform as if it were an even periodic function or an odd periodic. Let's do one example just so you can see how this is done. Okay. So let's consider the half function f of t is equal to t squared. Okay. This is defined on the interval from 0 to 1. So let's take this function and let's compute the even and odd half range expansions on the interval from -1 to 1. Okay. All right, so we're going to do two calculations here. So work first for the even range expansion, and the next for the odd. Let's do the even half range expansion first. Okay. And so for the even half range expansion, we still follow the same rules for our typical even and odd function. Okay. And so for an even function, we know that Bn is equal to 0. Okay, so we're not even going to compute Bn because we know it's going to be 0 because we're assuming the function is even. Okay. And so all we have to do is compute A0 and An. Okay. All right, so the formulas we're going to use for this is slightly modified because they're going to be for a half period. Okay. Because technically our function is only defined from 0 to 1. So normally when we compute these coefficients, we go from minus L to L. But in this case, we're gonna go from 0 to L. And so it's gonna change some things about the formula a little bit. Okay. So let's start with A0. Okay. Normally our A0 formula is 1 over 2L, integral from minus L to L, f of t, dt. Okay. We have our mean value function. Okay. But we can't integrate from minus L to L because in this case the function is not defined at minus L. And so we're going to modify this a little bit. And so instead, our A0 is going to be an integral from, instead of minus L to L, is going to be from 0 to L. Okay. And the other modification we're going to make is that we're going to divide by L on the front instead of 2L. Okay. Since we're only integrating over a period of L. Okay. So let's go ahead and plug in for that. So our f of t in this case is t squared. Okay. So t squared dt. Our L here is 1, so we're going to take the integral from 0 to 1. And we're going to have 1 over 1 in front, which is just 1. Okay. We perform this integral, we get 1/3 t cubed, evaluated from 0 to 1, which is just 1/3. Okay. Any questions on this result here so far? Yeah, you want to be careful about this when you're doing even and odd half range expansion. Make sure you're only integrating over half. Okay. Okay. So similarly, we're going to make the same adjustment for an. So normally our function for an is 1 over L integral from minus L to L of f of t cosine n pi t over L t. Okay. So that's what it is normally. But just like up there, we can't integrate from minus L to L because our function isn't defined up to that point. We're pretending it is, but technically it's not defined out. Okay. So we need to adjust this formula too. So now instead of 1 over L, we're gonna have 2 over L. Okay. Integral 0 to L t squared, or excuse me, I had myself. Okay. It is t squared, but I'm writing the generic formula now. So f of t sine n pi L. Okay. And so let's go ahead and plug in for this particular problem. So it's going to be 2 over L. 2 over 1, excuse me. So L is 1. Integral from 0 to 1. Our f of t here is t squared, cosine of n pi t, divided by L, which is 1. The t. Okay. We have a little bit of a nasty integral here. So we have t squared cosine integral. So we've seen this integral, several times in this class. It just keeps coming up. I know you're probably sick of it, but it just is what it is, right? Quadratic functions and sinusoids. And remember, the way that we do this is by applying integration by parts multiple times. Oh. Or if you come to office hours, or if you've read the kind of the integration handout, a technique that I like to use is integration by table. And so it saves a little bit of writing, it saves a little bit of time, but essentially that integration by table is just integration by parts multiple times. Okay. Okay, so I'm not going to go through the details of this again because we've done this integral so many times in this class already. Okay, but the result of this is so after integral and simplifying, we get an is equal to minus 4 over n pi squared cosine of n. Okay. And so now that we have a0 and we have an, we can form the function f of t just by plugging in different values of n. All right, any questions on this result here? All right, so that's the even half range expansion. And so, when they ask you for the even half range expansions, I'm looking for a0 and an. Bn is 0 for the even one. Now let's do the odd half range expansion, or at least I'll show you how to set it up. Just because I want to get to Fourier transforms. Okay. And so for the odd half range expansion, we're assuming basically our function is going to take an odd form. And so a0 and an are going to be 0. But we're not even going to bother computing them. And so, that saves us some time. And so the only thing we're going to compute here is bn. And so just like part A of this problem, we need to modify this a little bit because we're only given a half function. We're not given the full periodic function. Because normally our formula for Bn is 1 over L integral from minus L to L f of t sine of n pi t divided by L dt. Okay. And so we're going to modify this to only be for the half period. So this will be 2 over L integral from 0 to L f of t sine n pi t L. So make sure, when you're doing half range expansions, you do the one on the right. Because if you actually use the first one for this one and you assume it's t squared from minus 1 to 1, you're going to end up with Bn is equal to 0 because t squared, the unbounded version of t squared is just an even function. And so, but we're looking and we're assuming that we have kind of an odd half range expansion. So we have kind of an odd version. Okay, so let's go ahead and plug in for this problem. And so we have 2 over 1 integral from 0 to 1. Our t squared here, or f of t is t squared. And then we have sine of n pi t dt. Okay. Okay. So once again, we're given this kind of this ugly integral here. So we have to integrate this by parts. or integrate it by table, okay, whichever one you're more comfortable with. Okay. It is tedious, it does take some time, but it's definitely good to practice this. Okay. And so if you go through those, you end up with the following result. So after integrating and simplifying, we end up with the following expression. So we have Bn equal to 2 times minus 1 over n pi sine pi plus 2 n pi cubed sine n pi . Okay. And so once again, you can plug in different values of n. That's going to give you the different Bn coefficients, and you can plug that into the expansion for the function. Okay. All right. So that's half range expansion. So I think on the homework I only gave you 2 or 3 of them. But half range expansion is going to take a while because you have to do both the even version and the odd version of it. Okay. So don't underestimate the last problem. The last problem, I think it may look short, but I think that's one of the more time consuming ones. So make sure you kind of give enough time for that. It's going to be have to do both the even and the odd. It's a lot of integration. Okay. All right, any questions on this before you move on to Fourier transforms? Okay. All right, okay, so that's it for Fourier series, and so that's everything in homework 5. And so homework 5 is pretty jam-packed. There's a lot going on there. But definitely give it a try and then let me know if you have any issues. And so the last topic that we're going to cover before we take the second midterm is closely related to Fourier series, but it's called Fourier transforms. Okay, so it's related, but a little bit different. Okay. All right, so far, everything that we've covered with Fourier, we've done what's called the discrete Fourier series. Okay. And so what I mean by discrete is that our Fourier series, it does, we do have an infinite summation there, right? So our Fourier series has an infinite summation, but we only are really examining kind of integer multiples of a certain frequency. Okay. Let me write out our typical Fourier series again. So we have f of t equal to a0 plus infinite summation n is equal to 1 to infinity of an sine of n pi t l plus bn sine of n pi t. Okay. And so remember we talked about at the beginning of class today, that the coefficients and the frequencies here are closely related, right? Where the frequency of our expansion given by these terms here. Okay. And so the key characteristic here is that, yes, we're able to cover a lot of frequencies, right? And so because our summation is infinite here, okay, as long as n keeps increasing, we're going to cover a lot of different frequencies, right? But, the frequencies that we cover are only integer multiples of pi over L, basically. Okay? So since And so if we're only interested in those frequencies, like that's okay. But a lot of times, we're interested in looking at all frequencies, right? So, everything that's in between. Okay? And so in those situations, when we want to look at other frequencies, we're going to need a different mathematical tool in order to examine it. And a lot of times, we are interested in frequencies in between those integer multiples, right? And so, let's bring up the example of sounding, because that's kind of the most tangible example, right? And so, as I'm speaking here, I'm getting a lot of frequencies that are coming out of my mouth, right? And so if we want to kind of get a full picture of all the different frequencies that my voice is composed of, we need more than just the integer multiples, right? So we need a broad range of frequencies. So, we'd have to look at all the frequencies between, maybe the lowest frequency for human voice and the highest frequency. And what you'll see is that, if you actually break down the frequencies, then, there's kind of a very broad spectrum. Okay. Another situation where we would want to kind of have a different tool is if we want to look at non-periodic functions. But for our Fourier series, we've basically just been limiting ourselves to functions that kind of repeat naturally, right? So they kind of repeat on their own. Okay? Or in the worst case, for half-range expansions, we just pretend that they're okay. But in kind of the broader kind of area of the signals and functions that you can find out in the wild, there are a lot of non-periodic functions that you would want to look at. Okay? And you want to look at their frequency characteristics. Okay? Which sounds weird, right? And so, when you think of frequency, normally you think of like a function that's already kind of naturally periodic. But even for non-periodic functions, you can look at it, you can look at those kinds of functions from a frequency perspective, and I'm learning a lot of interesting information about them. Okay. That last where there's information, and just tried to squeeze it in. I got greedy, but it didn't work out. Okay. And so this tool, of course, is going to be Fourier transforms. That's kind of the title of these notes. And so we're going to learn about how to actually compute it and kind of what are its applications. Okay? And so typically when you say Fourier, kind of out, I would say out in the wild, so out in practice, in industry and kind of practical applications, most people think of the Fourier transform. The Fourier series, it's useful for it definitely has its uses, but for a lot of times it's kind of a stepping stone towards the Fourier transform. Okay, and I will say that our treatment of Fourier transforms in this class is going to be very brief, and so these lecture notes are actually a little bit shorter than my typical lecture notes, and there's a lot more to learn about it. But the Fourier transforms, I'm basically going to be teaching the basics and talking about some of the more interesting applications and interesting phenomena that are associated with it. Okay. Any questions on this so far? Okay. All right. So let's take a look at how we actually. And so our first order of business is to take our Fourier series and derive what's known as the Fourier integral. So that's going to be our first step to getting the Fourier transform. All right, so let's start with our Fourier series representation. F of t for the Fourier series is equal to A0 plus infinite summation and is equal to 1 to infinity an cosine of. Normally we do n pi t over L, but I'm just going to simplify it here. So I'm going to say omega n t plus bn sine omega n, okay, where omega n equals to n pi over L. Okay, so this is our usual infinite summation, right? So it's our Fourier series with discrete frequencies. Okay? And so in order to get an integral from this expression, what we need to do is we need to take the limit of this function as L approaches infinity. So we're basically turning our periodic function into a non-periodic function. Okay? Okay, and so to do that, we need to plug in for the coefficients here. And so we have A0, where A0 is 1 over 2L, integral from minus L to L, f of t dt. Okay. An is equal to 1 over L, integral from minus L to L, f of t, sine of, and t, bn, 1 over L, integral from minus L to L, f of t, sine, omega n t. Remember, omega n is given by n pi over L. All right, so let's go ahead and plug these in. We have these coefficients, and so let's go ahead and plug into our Fourier series up there. Okay. So we have f of t, 2. First, we have a0, so a0 is going to be 1 over 2l. Integral from minus l to l, f of t plus. I'm going to take 1 over l, I'm going to factor it out in front. So we have 1 over l. Okay. Infinite summation of cosine and t integral of f of t sine of omega n t plus sine omega n t integral f of t sine omega n t, and both these integrals are from minus l to l. Okay. So far, this is just the Fourier series. We haven't done any limits. We haven't done any integrals. This is just kind of what the Fourier series actually looks like, right? So when we compute the coefficients, we're computing those 3 integrals, except that, we don't usually put it in with the Fourier series just because it kind of gets complicated. Okay, so at this point, I'm going to do something a little bit strange. This is going to be a little bit out of left field. I'm going to bring in a new variable. It's not exactly a new variable. It's just kind of a different way of looking at these things. So let's define. Let's define a new variable called delta omega. And what this delta omega represents, remember, for the Fourier series, we're looking at discrete frequencies, right? So the frequencies are separated by, integer, okay? Or an integer multiple of them. And so what this delta omega, what this is going to represent is the difference in discrete frequencies of the Fourier series. And so this is defined as omega, we'll say omega n plus 1 minus omega n. Okay. So this is n plus 1, that's pi over L. It's n pi over L. Okay. We're just using our formula for omega n that was above, and then just kind of extrapolating for omega n plus 1. Okay, so we're plugging n plus 1 for that. Okay. And so if you do the subtraction here, the n terms are going to cancel out. And so all you get is just pi over L. So what this tells us is that, for a typical Fourier series, each frequency or each successive frequency in the series is separated by this amount right here. And so the difference between omega 1 and omega 2 is going to be pi over L. Okay. And so from this expression here, we can say that our new variable delta omega is pi over L. I'm going to rearrange this a little bit. So I'm going to move the pi to the bottom. And so we get delta omega over pi is equal to 1 over L. Okay. So this is important because if you look at our expression for the Fourier series above, we have 1 over L that shows up on the infinite summation. Okay. And so the reason we're doing this, now that we can take this. So now we have a formula for 1 over L. And we're going to plug it in for this in this spot right here. Okay, so let's see what that looks like. So after we plug that in, plugging that in, we get f of t. I'm going to leave the first term alone, and so the constant term, I'm going to leave the 1 over L there. We have 1 over 2L to go from minus L to L of f of t plus 1 over pi. Okay. The delta omega, I'm going to move inside. You'll see in a moment. The infinite summation from n is equal to 1 to infinity, cosine omega n t times delta omega integral minus L to L f of t sine of omega n t plus sine omega nt delta omega integral from minus L to L of f of t sine omega n t. Okay. So it's a very complicated expression, but don't worry, it's going to simplify a lot in just a second. Okay. And so what we're going to do with this monstrosity, okay, is we're going to simplify it. And so the way we're going to simplify it is we're going to take the limit. We're going to take the limit as L approaches infinity. So this is going to do a few things. And so it's going to be kind of a chain reaction of multiple things happening. Okay. First of all, let's look at the constant term. And so let's look at this first term out in front here. Okay. If you take the limit as L approaches infinity, then that 1 over 2L in front is just going to go to 0, right? So you have 1 over infinity, that's basically 0. Okay. This goes away. This goes away in the limit that L approaches infinity. Okay. And that's typical of a Fourier transform. So for the Fourier transform, we don't really look at the mean value. We look at just the frequency characteristics. Okay. Okay. The next thing we're going to look at is this combination right here. Okay. And so in the limit as L approaches infinity, okay, remember delta omega had an L in it as well, right? And so in this limit, this delta omega is going to get really small, but we're not going to cancel it out. Okay, so what we're going to say instead is that delta omega is going to become so small, it's going to become infinitesimally small. So that delta omega is going to turn to d omega, okay? And this infinite summation is going to turn into an integral. Okay. All right. So I know it's 9:45, but let me just kind of write out the final thing here, and then we'll take off. Okay. And so if we perform those two simplifications, then our f of t here is a lot simpler. So we have 1 over pi integral 0 to infinity of cosine omega t integral. Since we took the limit as L approaches infinity, now this inner integral goes from minus infinity to infinity. F of t cosine omega t dt, okay, plus sine omega t integral infinity f of t sine omega t t, and this entire thing here is integrated by d. Okay. Okay. And so that right there is known as our Fourier integral. Okay, and so it's basically the our Fourier series, but kind of generalized for an infinite period. Okay, and so inside this Fourier integral is our Fourier transform, but I think we'll talk about that next. Okay, so Thursday we'll pick it up right here. We'll kind of examine this Fourier integral a bit more, and we'll see how that leads to our Fourier transform. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. It looks like it's pretty wet and gloomy out there, so stay dry. And I will see you guys on Thursday. So for this one, we can so it'll be getting steady as no translation. No, I was doing that one when you're leaving. That should keep going. Yeah. I should sit here. Yeah. And I also heard yeah.